start by understanding what an inductor actually is. An inductor is a passive electrical component that stores energy in a magnetic field when electric current flows through it. It's typically made by winding a wire into a coil, and you'll find inductors in many electronic devices. Inductors are fundamental in circuits for managing current and voltage, especially in filtering, tuning, and energy storage applications. As we move forward, we'll explore how inductors work, their key properties, and why they're so important in electronics. Inductors are usually constructed by winding a conductive wire, often copper, into a coil. This coiled shape is crucial because it enhances the magnetic field generated when current passes through. The core of the coil can be air or a magnetic material like iron, which affects the inductor's properties. The number of turns in the coil, the material of the core, and the thickness of the wire all influence how the inductor behaves in a circuit. Next, let's see how this structure leads to the unique behavior of inductors. An electric current flows through the coil of an inductor. It creates a magnetic field around it. This magnetic field is the key to how inductors store energy. The strength of the magnetic field depends on the amount of current, the number of coil turns, and the core material. If the current changes, the magnetic field also changes, which leads to some interesting effects in circuits. In the next scene, we'll discuss how this changing magnetic field influences the flow of current. Inductance is the property of an inductor that quantifies its ability to store energy in a magnetic field. It's measured in Henry's H. The higher the inductance, the more energy can be stored for a given current. Factors like the number of coil turns, core material, and coil size all affect inductance. Inductance determines how strongly an inductor resists changes in current. Next, we'll see how this resistance to change plays a role in electronic circuits. One of the most important behaviors of an inductor is its tendency to oppose changes in the current flowing through it. When the current increases or decreases, the inductor generates a voltage that resists this change. This property is known as self-inductance. It's why inductors are so useful in circuits that need to smooth out fluctuations or filter signals. In the next scene, we'll look at the mathematical relationship that describes this behavior. Behavior of inductors is governed by Faraday's law of electromagnetic induction. This law states that a changing magnetic field induces a voltage in a coil. The faster the current changes, the greater the induced voltage. This is why inductors resist sudden changes in current. Faraday's law is fundamental to understanding how inductors work in all kinds of electronic circuits. Next, we'll see how this principle is used in practical application. Inductors store energy in their magnetic field when current flows through them. The amount of energy stored depends on the inductance and the current. This energy can be released back into the circuit when the current decreases. This property makes inductors essential in power supplies and energy storage systems. In the next scene, we'll explore some common uses of inductors in everyday electronics. Inductors are widely used in power supply circuits. They help smooth out voltage and current, reducing noise and providing stable power to sensitive components. In switching power supplies, inductors temporarily store energy and release it as needed, improving efficiency. Their ability to filter and regulate makes them indispensable in modern electronics. Next, we'll look at how inductors are used in signal processing. Inductors are key components in filters that separate signals of different frequencies. In low-pass filters, inductors block high-frequency signals while allowing low-frequency signals to pass. This is crucial in audio equipment, radio receivers, and many other devices. By combining inductors with capacitors, engineers can design circuits that precisely control which signals are allowed through. Next, we'll discuss inductors in tuning circuits. Inductors are used in tuning circuits such as those found in radios. By pairing an inductor with a capacitor, you can create a resonant circuit that selects a specific frequency. This allows radios to tune into different stations. The ability to select frequencies is also important in wireless communication and signal processing. Next, we'll look at the different types of inductors you might encounter. Air core inductors use air as the core material inside the coil. They are simple in construction and don't suffer from core losses, making them ideal for high-frequency applications. However, they usually have lower inductance compared to inductors with magnetic cores. Air core inductors are commonly used in radio frequency circuits. Next, let's explore iron core inductors and their advantages. Iron core inductors use a core made of iron or other magnetic materials. This increases the inductance and allows the inductor to store more energy. They are often used in power supplies and audio equipment where higher inductance is needed. However, they can suffer from core losses at high frequencies. Next, we'll look at ferrite core inductors and their unique properties. Ferrite core inductors use a core made from ferrite, a type of ceramic material with magnetic properties. Ferrite cores are excellent for high-frequency applications because they have low core losses. These inductors are widely used in radio frequency circuits, transformers, and switching power supplies. Their efficiency and performance make them a popular choice in modern electronics. Next, let's discuss the main parameters that define an inductor. Several parameters define an inductor's performance. These include inductance measured in Henrys, current rating, resistance, and quality factor Q. The inductance determines how much energy can be stored, while the current rating tells you how much current the inductor can handle safely. Resistance affects efficiency, and the quality factor measures how well the inductor performs at a given frequency. Next, we'll see how these parameters are specified in datasheets. Selecting an inductor for a project, engineers consult datasheets. These documents list all the key parameters, including inductance, current rating, resistance, and physical dimensions. Understanding these specifications helps ensure the inductor will perform as needed in the circuit. It's important to match the inductor's ratings to the requirements of your application. Next, let's look at how inductors are represented in circuit diagram. Circuit diagrams, inductors are represented by a coiled wire symbol. Sometimes the symbol includes lines or dots to indicate the type of core material. Recognizing these symbols is essential for reading and designing electronic circuits. The symbol helps engineers quickly identify where inductors are used and how they interact with other components. Next, we'll discuss how inductors are connected in series and parallel. When inductors are connected in series, their total inductance is the sum of the individual inductances. This configuration is used when a higher total inductance is needed. Series connections are common in filter circuits and energy storage applications. However, the total resistance also increases, which can affect efficiency. Next, we'll see what happens when inductors are connected in parallel. A parallel connection, the total inductance is less than the smallest individual inductor. This setup is used when a lower total inductance is needed, or to share current between inductors. Parallel connections are useful in certain filter designs and power distribution systems. The current divides among the inductors, which can help manage heat and improve reliability. Next, we'll discuss mutual inductance and its significance. Mutual inductance occurs when two inductors are placed close together, and the magnetic field from one affects the other. This principle is the basis for transformers, which transfer energy between circuits using magnetic fields. Mutual inductance is measured in henries, just like self-inductance. It's a key concept in power transmission and signal coupling. Next, we'll look at how transformers use mutual inductance. Transformers are devices that use mutual inductance to transfer electrical energy between two or more coils. They can step voltage up or down, making them essential in power distribution. Transformers are found in everything from power grids to phone chargers. Their operation relies on the principles of inductance and magnetic fields. Next, we'll discuss the limitations and losses associated with inductors. Inductors with magnetic cores can experience core losses, especially at high frequencies. These losses are caused by hysteresis and eddy currents in the core material. Core losses reduce efficiency and can generate heat. Engineers choose core materials carefully to minimize these effects. Next, we'll look at another type of loss, copper loss. Copper loss refers to the energy lost as heat due to the resistance of the wire in the inductor. The longer and thinner the wire, the higher the resistance and the greater the loss. Copper loss is especially important in high current applications. Engineers often use thicker wire or special materials to reduce these losses. Next, we'll discuss how inductors are affected by external magnetic fields. Inductors can be influenced by external magnetic fields, which may induce unwanted voltages or noise. Shielding and careful placement in a circuit can help reduce these effects. In sensitive applications, engineers use special shielding materials or layouts to protect inductors from interference. Next, we'll look at how temperature affects inductor performance. Temperature changes can affect an inductor's performance. High temperatures may increase resistance and reduce efficiency, while extreme cold can make materials brittle. Some inductors are designed to operate in harsh environments using special materials to maintain performance. Next, we'll discuss how inductors are tested and measured in the lab. Engineers test inductors using specialized equipment to measure inductance, resistance, and quality factor. These tests ensure the inductor meets its specifications and will perform reliably in a circuit. Testing is especially important for high-precision or safety-critical applications. Next, we'll look at how inductors are manufactured. Inductor manufacturing involves winding wire onto a core, assembling the core, and adding insulation or protective coatings. Automated machines are often used for mass production, ensuring consistency and quality. After assembly, inductors are tested and packaged for shipment. Manufacturing techniques continue to evolve, improving performance and reducing costs. Next, we'll discuss the miniaturization of inductors for modern electronics. As electronic devices become smaller, inductors must also shrink in size. Advances in materials and manufacturing allow for compact inductors that still provide high performance. Surface mount technology enables inductors to be placed directly on circuit boards, saving space and improving reliability. Miniaturization is key for smartphones, laptops, and wearable devices. Next, we'll look at the role of inductors in wireless charging. Inductors play a crucial role in wireless charging systems. They create and receive magnetic fields that transfer energy between devices without physical connections. This technology is used in smartphones, electric toothbrushes, and even electric vehicles. Wireless charging relies on the principles of inductance and resonance. Next, we'll discuss the use of inductors in radio frequency identification (RFID) system. RFID systems use inductors in both the reader and the tag. The reader generates a magnetic field which induces a current in the tag's coil. This allows for wireless communication and identification of objects. Inductors in RFID systems must be precisely designed for efficient energy transfer and signal detection. Next, we'll look at the use of inductors in audio equipment. Inductors are used in audio equipment to filter signals, shape sound, and reduce noise. They help create smooth, high-quality audio by blocking unwanted frequencies. Inductors are found in speakers, amplifiers, and crossover networks. Their role is essential for delivering clear and accurate sound. Next, we'll discuss inductors in automotive electronics. Modern vehicles rely on inductors for many functions, including power management, noise suppression, and signal filtering. Inductors help ensure reliable operation of electronic control units, infotainment systems, and safety features. Their durability and performance are critical in the demanding automotive environment. Next, we'll look at inductors in renewable energy systems. Inductors are essential in renewable energy systems, such as solar inverters and wind turbines. They help convert and regulate power, ensuring efficient energy transfer and storage. Inductors also protect sensitive electronics from voltage spikes and fluctuations. Their role is vital in making renewable energy systems reliable and efficient. Next, we'll discuss the challenges of designing inductors for high-frequency circuits. Designing inductors for high-frequency circuits presents unique challenges. Core losses, parasitic capacitance, and skin effect can all impact performance. Engineers use special materials and construction techniques to minimize these effects. Careful design ensures inductors work efficiently in radio, communication, and high-speed digital circuits. Next, we'll look at the future trends in inductor technology. Future of inductor technology includes advances in materials, miniaturization, and integration with other components. Researchers are developing new core materials with lower losses and higher efficiency. Integrated inductors are being built directly into chips, saving space and improving performance. These trends will enable even more compact and powerful electronic devices. Next, we'll summarize the key points about inductors. Sum up, inductors are passive components that store energy in a magnetic field. Their unique properties make them essential in power supplies, filters, tuning circuits, and many other applications. Understanding how inductors work, their types, and their key parameters is crucial for anyone working with electronics. In the next scenes, we'll answer some common questions about inductors and clear up a few misconceptions. People often wonder why inductors are needed when capacitors also store energy. The key difference is that inductors store energy in a magnetic field while capacitors store it in an electric field. Each has unique properties and uses in circuits. Another common question is about the safety of inductors. While they are generally safe, large inductors can store significant energy and should be handled with care. Next, we'll address some misconceptions. Common misconception is that inductors only work with DC current. In reality, inductors are most effective with AC or changing currents, where their ability to oppose changes is most useful. Another myth is that all inductors are large and bulky, but modern technology allows for very small, efficient inductors. Next, we'll look at some tips for working with inductors in your own projects. When working with inductors, always check the datasheet for ratings and limitations. Make sure the inductor can handle the expected current and voltage. Pay attention to layout and placement to avoid interference from external magnetic fields. Using the right type of inductor for your application will ensure reliable performance. Next, we'll discuss safety precautions when handling inductors. While most inductors are safe to handle, large inductors can store significant energy and may produce high voltages if disconnected suddenly. Always discharge large inductors before handling and use proper insulation. In high-power circuits, follow safety guidelines to prevent accidents. Next, we'll look at resources for learning more about inductors. There are many resources available for learning more about inductors, including textbooks, online courses, and electronics forums. Experimenting with simple circuits is a great way to gain hands-on experience. As you build your knowledge, you'll discover new ways to use inductors in your own projects. Next, we'll explore some famous inventions that rely on inductors. Many groundbreaking inventions rely on inductors, such as radio transmitters, transformers, and electric motors. These devices have shaped modern technology and continue to evolve. Understanding inductors gives you insight into how these inventions work and how you can innovate in the future. Next, we'll look at the role of inductors in emerging technologies. Inductors are finding new roles in emerging technologies like wireless power transfer, electric vehicles, and advanced communication systems. Their ability to manage energy and signals makes them vital for innovation. As technology advances, inductors will continue to be a key component in shaping the future. Next, we'll discuss how to choose the right inductor for your project. Choosing the right inductor depends on your application's requirements. Consider factors like inductance, current rating, size, and core material. Consult datasheets and application notes for guidance. Testing different inductors in your circuit can help you find the best match. Next, we'll look at troubleshooting common inductor problems. Common inductor problems include overheating, noise, and unexpected circuit behavior. Overheating may indicate excessive current or poor ventilation. Noise can result from external magnetic fields or poor layout. Careful design and testing can help prevent these issues. Next, we'll wrap up with a final summary and key takeaways. Inductors are fascinating and versatile components that play a vital role in electronics. From energy storage to signal processing, their unique properties enable countless applications. By understanding the concept of inductors, you'll be better equipped to design, troubleshoot, and innovate in the world of electronics. Keep exploring and experimenting, and you'll unlock even more potential with inductors in your projects.